Our planet Earth, a world of vibrant life and dramatic landscapes. But have you ever pictured what our world looked like millions of years ago? Imagine a time when continents were mashed together, forming a single colossal landmass. This was the supercontinent Pangaea. Fasten your seatbelts as we embark on a thrilling expedition through time, exploring the age of Pangaea and beyond. We'll delve into geological history, unraveling the mysteries of continental drift and plate tectonics. So let's dive in and uncover the story of Pangaea and beyond. The idea that continents might move is not new. In the 16th century, mapmakers noticed the coastlines of South America and Africa fit together. But it wasn't until the early 20th century that Alfred Wegener proposed the theory of continental drift. Wegener envisioned a time when all continents were united in Pangaea. According to Wegener, Pangaea broke apart over millions of years, forming today's continents. His theory was met with skepticism because it lacked a mechanism to explain the movement. Despite resistance, Wegener gathered evidence from geology, paleontology, and climatology. He pointed to matching rock formations and fossil records on now separated continents. Alfred Wegener faced an uphill battle convincing the scientific community of his theory. His background as a meteorologist made him an outsider. Geologists were reluctant to accept such a radical idea from an amateur. Critics argued his evidence was circumstantial and demanded a plausible mechanism. Wegener continued to refine his theory, publishing updated editions of his book. Though he died in 1930, his work laid the groundwork for the theory of plate tectonics. Imagine Earth 300 million years ago. In place of modern continents lay Pangaea, a colossal landmass surrounded by Panthalassa. Life on Pangaea was as different as its geography. The supercontinent's interior experienced extreme temperatures. Vast deserts spread across the land, while lush forests thrived along the coasts. The fossil record tells tales of giant insects and bizarre reptiles. Pangaea was shaped by powerful geological forces, with volcanoes and earthquakes reshaping the landscape. This period, known as the Permian, was a time of flourishing life and dramatic upheaval. Around 200 million years ago, Pangaea began to break apart. Convection currents in the mantle exerted pressure on the supercontinent. Cracks appeared in Earth's crust and volcanoes erupted along these rifts. The landmass began to split, with North America rifting from Africa and South America from Antarctica. New oceans were born as water filled the widening gaps. The Atlantic Ocean began to grow, while other ancient oceans closed as continents collided. The breakup of Pangaea was a slow process unfolding over millions of years. It was a time of dramatic transformation, altering the planet's geography and the course of life. Earth's continents embarked on long, slow journeys across the globe. The separation of continents had profound consequences for Earth's oceans and climate. New ocean basins altered the planet's system of ocean currents. The breakup of Pangaea influenced global sea levels, causing them to rise and fall. The collision of continents gave rise to awe-inspiring mountain ranges. The Himalayas, for example, were formed by the collision of the Indian subcontinent with Asia. As continents drifted to new latitudes, their climates changed dramatically. These climatic shifts forced plants and animals to adapt to new environments or face extinction. The theory of plate tectonics, which emerged in the 1960s, revolutionized our understanding of Earth's geological processes. This groundbreaking theory provided a comprehensive explanation for the movement of Earth's lithospheric plates and the dynamic nature of our planet's surface. Before plate tectonics, Alfred Wegener's theory of continental drift suggested that continents moved across the Earth's surface. However, it lacked a convincing mechanism to explain how this movement occurred. Earth's outer layer, known as the lithosphere, is composed of a mosaic of rigid plates. These plates are like pieces of a giant jigsaw puzzle, fitting together to cover the entire surface of the Earth. Beneath the lithosphere lies the asthenosphere, a semi-fluid layer that allows the rigid plates to move. The asthenosphere's plasticity is crucial for the movement of the lithospheric plates. These plates are in constant motion, albeit at a slow pace. They move a few centimeters per year, driven by forces deep within the Earth. The primary driving force behind plate movement is the convection currents in the mantle. These currents are generated by the heat from the Earth's core, causing the semi-fluid mantle to circulate. There are 7 major tectonic plates: the African, Antarctic, Eurasian, Indo-Australian, North American, Pacific, and South American plates. In addition to these, there are numerous smaller plates that also play a significant role in Earth's geology. Each of these plates moves at a rate of a few centimeters per year. While this may seem slow over millions of years, these movements have profound effects on the Earth's surface. Plate boundaries are the sites of intense geological activity. It is at these boundaries that we find the majority of the world's earthquakes, volcanoes, and mountain-building events. At divergent boundaries, plates move apart from each other. This movement creates new crust as magma rises from the mantle to fill the gap, forming mid-ocean ridges and rift valleys. At convergent boundaries, plates collide with one another. This collision can result in the formation of towering mountain ranges, such as the Himalayas, or the creation of deep oceanic trenches through the process of subduction. In subduction zones, one plate is forced beneath another into the mantle, where it melts and can lead to volcanic activity. This process is responsible for some of the most powerful and destructive volcanic eruptions on Earth. Transform boundaries occur where plates slide past each other horizontally. The friction between the plates prevents them from sliding smoothly, leading to the buildup of stress and eventually earthquakes. The San Andreas Fault in California is a prime example of a transformed boundary. This fault is notorious for its seismic activity, which has caused significant earthquakes in the region. Plate tectonics explains the dynamic processes that shape our planet today. From the creation of new crust at divergent boundaries to the destruction of old crust at subduction zones, the movement of tectonic plates is a fundamental force in Earth's geology. Understanding plate tectonics also helps us to interpret the geological history of our planet. By studying the movement of plates over time, scientists can reconstruct past continental configurations and gain insights into the processes that have shaped Earth's surface. Modern geological research continues to explore the complexities of plate tectonics. Advances in technology such as satellite measurements and deep-sea exploration have provided new data that enhance our understanding of these processes. Looking to the future, the study of plate tectonics is crucial for predicting geological events and understanding how Earth's landscape will continue to evolve. This knowledge is essential for mitigating natural disasters and planning for a sustainable future. Educational resources and classroom learning about plate tectonics play a vital role in raising awareness about Earth's dynamic nature. By educating future generations, we can ensure that the knowledge of these processes is passed on and applied to address global challenges. Global collaboration in geological research is also key. Scientists from around the world work together to share data, conduct experiments, and develop models that improve our understanding of plate tectonics and its impact on our planet. Visualizing Earth's inner workings through comprehensive geological models allows us to see the interconnectedness of various processes. These models help us to appreciate the complexity and beauty of our planet's geology. As we continue to unlock the secrets of Earth's inner workings, we celebrate the scientific discoveries and advancements in Earth sciences that have brought us to this point. The journey of understanding our planet is ongoing, and each new discovery brings us closer to a deeper appreciation of the world we live in. The story of Pangaea and plate tectonics is supported by tangible evidence. Identical fossil species are found on continents now separated by vast oceans. For example, Mesosaurus fossils are found only in South America and Africa. Similarly, Glossopteris fossils are found in South America, Africa, India, Antarctica, and Australia. Matching rock formations and mountain belts on separated continents tell a similar story. The Appalachian Mountains of North America are geologically similar to the Caledonian Mountains of Scotland and Scandinavia. Paleomagnetism, the study of magnetic signatures in ancient rocks, helps reconstruct past movements of the continents. These pieces of evidence support the existence of Pangaea and the theory of plate tectonics. Plate tectonics helps us understand the dynamic processes shaping our planet today. Earthquakes, volcanoes, and mountain building occur at plate boundaries. Earthquakes are caused by the sudden release of energy along faults. The most powerful earthquakes occur at convergent and transform boundaries. Volcanoes are vents where molten rock, ash and gases escape from the interior. The Ring of Fire, a zone of intense volcanic and earthquake activity, encircles the Pacific Ocean. Mountain building is driven by the collision of continental plates. The Himalayas, the Alps, and the Andes are examples of mountains formed by plate collisions. These mountain ranges are constantly reshaped by erosion, weathering, and plate tectonics. The story of Pangaea and plate tectonics is fundamental to understanding our planet today. Plate tectonics continues to shape our world, from earthquakes and volcanic eruptions to mountain building and climate regulation. Understanding plate tectonics helps us prepare for natural disasters and manage resources. Pangaea's breakup shaped the continents and oceans we know today. The continents are still on the move, drifting across Earth's surface. The story of Pangaea is still being written in the rocks beneath our feet and the ever-changing face of our planet.